Okay, we'll now define a topological space. We have already motivated this as being the right definition for capturing continuity and also both being well behaved with respect to various constructions and capturing them as examples. So let's suppose topological space. So let's suppose we have X as a set, be a set. Okay. So then a topology on X is a collection of sets. We'll call them open subsets. A collection omega of subsets of X. We're going to call them open sets such that a few properties have to be satisfied. First of all, unions of set in omegas are in omega. So if we have U alpha in some index set I is a collection of subsets of omega, that is of open sets, then the union of alpha in I of U alpha is also in omega. Okay, so this is if you, for example, have a sequence of sets, then each of which is in omega, then their union is also in omega. So union of open sets is union. This is to allow uncountable collections, just basically arbitrary collections of sets. Okay, but with intersections things are not so good, because for example with open intervals you can intersect them and get just a point. So you don't have intersections of open sets in necessarily open, but if we have finite intersections, if u1, u2, un are in omega, then the intersection, let's say I equals 1 to n of ui is in omega. Okay, so this is the case where we have by the way, by induction, so if we have this case, so let me make that remark here. So let's number these 1, 2, and then property 3 is coming up. Okay, and so remark 2 is equivalent to assuming well, 2 prime, let me just write it. Suppose we have u and v in omega, then u intersection v is in omega. Okay. Given property 3 in one extreme case, which we will discuss in a moment, but 2 is equivalent to saying if a pair of sets is in omega, then their intersection is omega, because from that by induction we can deduce the 2 as stated there, and conversely specialize for n equals 2. Okay. By the way, the induction doesn't quite work in one case, but that is covered by the third property which I'm going to mention, which is that both phi and x are contained in omega. So the whole space is open and the empty set is open. Okay, so strictly speaking, these follow from the previous axioms, because an empty union gives you the identity with respect to union, which is the empty set, and an empty intersection gives you everything, which is the identity with respect to intersection of subsets of a given set. For abstract sets, there is no identity for intersection. So this is this would really follow from 1 and 2 if we allow the degenerate cases. And indeed, when I'm trying to say that 2 is equivalent to for pairs of sets, induction shows for at least one set, not the degenerate case of 0 sets. Okay, so empty set and the whole space are in omega. It's closed under finite intersections or equivalently intersections of pairs, and closed under arbitrary unions. This is what topology on X is, and the pair X comma omega is called a topological space. And I have already mentioned, but let's write it down, sets u in omega are called the open sets. So the open sets in the topology. So the open sets are exactly the sets which are elements of this topology. Okay, the members of the topology are open sets. So this is the formal definition. I have motivated it. It will get clearer and clearer as we see examples and properties and use these very many times. So in this video, we'll only see a couple of generic examples where we'll see the properties true. And then in the next lecture, we'll turn to the more detailed and interesting examples. Of course, throughout the course, we'll keep seeing more and more examples, since constructing spaces is one of the key points in this topic. So the first examples we see are in some sense degenerate examples. Okay, so for these, let X be a set. Any set we can define two topologies on. We'll in fact define a third not too far in the future, and there are variants of that, but two important topologies. They're important in a way even though they're degenerate. First one is what is called a discrete topology. This is where we think of X as being a bunch of isolated points, all far away from each other. Okay, and so remember, a neighborhood, open set means it contains a neighborhood of any point. But a neighborhood of a point, if it's isolated, is just itself. So open set means given a point in the set, it contains a point in the set. That is of course true. Okay, so that means omega is the power set, is all subs, is, let me just write it this way, U in X. That's it. U is a subset. So it's the power set, often written as 2 to the power of X. Okay, or 0, 1 to the X, whatever you like. So this is the power set, all subsets. Now this is, since this is our first example, let's verify the properties. One, if we have a collection, remember this is saying if U alpha belongs to A is such that U alpha is in omega, okay, then of course union of alpha in A of U alpha is a subset. So U alpha belongs to omega, which means U alpha is a subset of X. Okay, so these are all subsets of X, of course, members of the topology. So then in the union of these is a subset of X, so union belongs to omega. Every subset of X is in omega. Sorry, I was about to say it belongs to X. Of course, it doesn't. Okay, so open sets are subsets of omega. They are all of them, but we don't use that here. Instead, we simply say they're subsets of X. They're members of omega, not subsets of omega. So their union is a subset of X, so it's in omega. How about the second one? The second one is that if suppose we have U1, suppose we have finite sets in omega. Well, again, there is nothing to show. Okay, then so these are all subsets of X. So U1 intersection UN is contained in X, which implies that U1 intersection UN is in omega. So this, since there was no condition other than being a subset, this is automatic. So the 3 is of course even easier. So 3 is saying, let me just state this and then say it's easy to recall. Phi belongs to omega and X in omega. And let me just say by definition, not of phi of X, but of by definition of omega. X is of course a subset of itself, and by the way, this subset includes equality. Yeah, so sometimes in elementary mathematics people try to distinguish between the two, but it doesn't make sense. It only makes life harder. So here we have a discrete topology. It's really no topology at all, in the sense that, as we will see when we see continuous functions, any function to the discrete spaces from a discrete topology is continuous. Okay, so the second one is the opposite extreme, indiscrete topology. Well, this has as few open sets as possible. Well, what is that? The property 3 says that empty set in X should be in omega. And so if I take omega to be exactly the empty set in X, then this is the indiscrete topology. Okay, this is as if all points were clustered together next to each other with no room to go away. At any scale, however you resolve them, you can't separate them. Okay, so here let's see why are these two properties true. 3 is true by definition, so I'm not going to bother to verify it. But 1 and 2 are not quite so simple here, but it's a straightforward exercise. So suppose U alpha. Suppose U alpha, this collection is such that U alpha is in omega for all alpha. Okay, so then we have two cases, case A. So each U alpha, so U alpha is phi or U alpha is all of x for all alpha in A. So the case A is that if U alpha is phi for all alpha, so then this will imply that union of U alpha is in union over alpha in A is also empty. So this is in omega. And the case B is that if U alpha is x for some alpha, that is the opposite of the first case, okay, then U alpha is going to be equal, then the union, okay, I won't try to squash in this sheet, we'll see the part 2 in the next page. Union of alpha in A of U alpha, this union, if one of them is x, they are all subsets of x, this is x, and this is also in omega. So what happens is if we have a collection of open sets, either they're all empty or one is not empty. But if one is not empty, then it's immediately all of x. Okay, so that in either case we see that we have the union being in x. Okay, and meanwhile let's see the part 2. Okay, so part 2 is suppose let u1 un belong to omega. Suppose we have finitely many sets contained in omega. Again we are going to split into cases. Okay, so this time we want to take with the intersection numbers. Okay, so but let's note just then ui is phi or ui is omega for each I. Sorry, not omega, it's x. Let me just check in the previous page if I said omega by mistake. No, u alpha is phi or it's x. So similarly ui is phi or ui is x for each I. Doesn't mean that one of these two cases holds for all i's. So some i's may have this case and some i's may have this case. Okay, now we split by cases again, but this time we note it's an intersection, so it tends to get smaller. Okay, so this time let's take our case as ui equals x for all I. So then u1 intersection un, so all of them are x, so this is in omega. And the second case is that ui is empty for some I. So this implies that u1 intersection un is going to be empty set, which is in omega. So we saw a couple of examples here. So what we have achieved here is given a definition which was partly motivated, and as I said, a large part of the motivation is it just works. So you'll learn it better and better and appreciate it by just checking that it works as we go along the way. But on the other hand, we have also seen a couple of examples where we simply worked with the definition and saw that they satisfy all the properties. Well, this one, of course, 3 is going to be, phi comma x belong to omega just for completeness. In this case, omega is exactly these two elements. So we worked with the definition and saw certain topologies are what satisfy the properties we had. Okay. A comment about the indiscrete topology is that functions from these are usually not continuous, we will see that, but functions to the indiscrete topology will always be continuous, because you can't distinguish between the points, so any two points go to basically the same point, so you will satisfy continuity. When we see the definition of continuity, we'll see this as an example. A second comment here is this is in a sense a bad space. It does not come from a metric space. So by passing to indiscrete topology, we have strictly generalized from metric spaces. This is not a good reason, because maybe we don't ever get the indiscrete topology, but indeed there are many very good examples where what we get does not actually come from a metric, good and important examples. So this would be a reasonable first example of something which shows our topology is more general than metrics.